Myself, P.S. Kayalvizhi, Assistant Professor, PG Department of Mathematics. I present on a topic Operation Research. First, let us see the general linear programming problem. Let Z be a linear function on R power n defined by Z equal to C1x1 plus C2x2 plus etc. Cn xn A11x1 plus A12x2 etc. A1n xn greater than or equal to or less than or equal to B1. A21x1 A22x2 etc. A2n xn greater than or equal to or less than or equal to B2 etc. AM1x1 plus AM2x2 etc. AMN xn greater than or equal to or less than or equal to Bn. Let and also xj greater than or equal to 0, j equal to 1 to etc. n. The problem of determining an n tuple x1, x2, etc. xn which makes z a minimum or maximum and satisfies the equation 1 and 2 is called the general linear programming problem. Next, let us see the objective function. The linear function z equal to c1x1 plus c2x2 plus etc. cn xn which is to be minimized or maximized is called the objective function of the general LPP. Next, constraints. The equation 1 are called the constraints of the general LPP. Non-negative restrictions. The set of inequalities 4 is usually known as the set of non-negative restrictions of the general LPP. Next, we see the definition of solution, feasible solution and optimum solution. An n tuple x1, x2, etc. xn of real numbers which satisfies the constraints of the general LPP is called the solution to the general LPP. Next, any solution to a general LPP which also satisfies the non-negative restrictions of the problem is called a feasible solution to a general LPP. Any feasible solution which optimize, that is minimize or maximize the objective function of a general LPP is called an optimum solution to the general LPP. Next, we see the canonical form. The general formulation of linear programming problem discussed in the previous section can always put in the following form. Maximize z equal to c1x1 plus c2x2 plus etc. cn xn subject to the constraints ai1x1 plus ai2x2 plus etc. ain xn less than or equal to bi. I varies from 1 to etc. m and x1, x2, etc. xn greater than or equal to 0. By making use of this elementary transformation, the form of LPP is called the canonical form of LPP. Then the characteristic of this form are the objective function is of maximization type. If it is a minimization problem, we have to make it to maximization by putting minimum z equal to minus maximum of z minus z. All the constraints are of less than or equal to type except for the non-negative restrictions. Then all the variables are non-negative. Next, we will see the standard form. The general LPP in the form maximize or minimize z equal to c1x1 plus c2x2 plus etc. cn xn subject to the constraints ai1x1 plus ai2x2 plus etc. ain xn equal to bi and I varies from 1 to etc. m x1 x2 etc. xn greater than or equal to 0 is known as the standard form. The characteristics of this form are all the constraints are expressed in the form of equation except for the non-negative restrictions. The right hand side of each constraint equation is non-negative. The inequality constraint can be changed into an equation by introducing a non-negative variable. The left hand side of such constraint, it is to be added slack variable if the constraint is of less than or equal to and subtracted, that is a surplus variable if the constraint is of greater than or equal to type. In matrix notation, the standard form of LPP can be expressed as maximize or minimize z equal to cx subject to constraints ax equal to b, x greater than or equal to 0, where x equal to x1, x2, etc. xn, c equal to c1, c2, etc. cn, b transpose equal to b1, b2, etc. bn, and a equal to matrix aij. I varies from 1 to m and j varies from 1 to n. Next, we see the definition of slack variables. If the constraints of the general LPP be summation j equal to 1 to n aij xj less than or equal to bi, then the non-negative variables xn plus I which satisfies the constraint, that is summation j equal to 1 to n aij xj plus xn plus I equal to bi are called slack variables. Next, we see the definition of surplus variables. Is the constraints of the general LPP be summation j equal to 1 to n aij xj greater than or equal to bi, the non-negative variables xn plus I which satisfies summation j equal to 1 to n aij xj minus xn plus I equal to bi are called surplus variables. Next, we will see the examples of general LPP. Rewrite in standard form the following linear programming problem. Minimize z equal to 2x1 plus x2 plus 4x3 subject to constraints minus 2x1 plus 4x2 less than or equal to 4, x1 plus 2x2 plus x3 greater than or equal to 5, 2x1 plus 3x3 less than or equal to 2, x1, x2 greater than or equal to 0 and x3 is unrestricted in sign. So, in first and third equations, as the constraints are in the form of inequalities, in first and third equation we have to introduce slack variables, that is x5 greater than or equal to 0 and x6 greater than or equal to 0, and surplus variables x6 greater than or equal to 0 in the constraints. Further, x3 is unrestricted in sign, so we make it to restricted, x3 equal to x3 dash minus x3 double dash, where x3 dash greater than equal to 0 and x3 double dash greater than equal to 0. Then the constraints of the problem becomes minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 dash minus x3 double dash minus x6 equal to 5, 2x1 plus 3 into x3 dash minus x3 double dash plus x3 equal to 2. The non-negative restrictions are x1 greater than equal to 0, x2 greater than equal to 0, x3 dash greater than equal to 0, x3 double dash greater than equal to 0, x5 greater than equal to 0 and x6 greater than equal to 0 and x4 greater than equal to 0. The objective function of the problem is converted into that of maximization by multiplying it by minus 1. Also, we assign a cost 0 to each slack or surplus variable. Thus, the revised objective function is maximize z star equal to minus 2x1 minus x2 minus 4 into x3 dash minus x3 double dash plus 0x4 plus 0x5 plus 0x6, where z star equal to minus z. The given LPP in standard form is maximize z star equal to minus 2x1 minus x2 minus 4x3 dash plus 4x3 double dash plus 0x4 plus 0x5 plus 0x6 subject to constraints minus 2x4 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 dash minus x3 double dash minus x6 equal to 5, 2x1 plus 3x3 dash minus 3x3 double dash plus x5 equal to 2, xj greater than equal to 0, j equal to 1, 2, 3 dash, 3 double dash, 4, 5, 6. Next, we see the another problem reduced to standard form. Maximize z star equal to 3x1 plus 4x2 plus 6x3 subject to constraints 2x1 plus x2 plus 2x3 greater than equal to 6, 3x1 plus 2x2 equal to 8, 7x1 minus 3x2 plus 5x3 greater than or equal to 9, x1 greater than or equal to 0, x2 greater than or equal to 0 and x3 is unrestricted in sign. Since the first and third inequalities are inequalities with greater than or equal to sign, we introduce surplus variables x4 greater than or equal to 0 and x5 greater than or equal to 0 in the respective inequalities. Further, x3 is unrestricted in sign. We write x3 equal to x3 dash minus x3 double dash, where x3 dash greater than or equal to 0 and x3 double dash greater than or equal to 0. Thus, the constraints of the given LPP are 2x1 plus x2 plus 2 into x3 dash minus x3 double dash plus x4 equal to 6, 3x2 plus 2x2 equal to 8, 7x1 minus 3x2 plus 5x3 dash minus x3 double dash plus x5 equal to 9. The objective function will be maximize z equal to 3x1 plus 4x2 plus 6x3 dash minus x3 double dash. The given LPP in standard form is maximize z equal to 3x1 plus 4x2 plus 6x3 dash minus 6x3 double dash plus 0x4 plus 0x5 subject to constraints 2x1 plus x2 plus 2x3 minus x3 2x3 dash minus 2x3 double dash plus x4 equal to 6, 3x1 plus 2x2 equal to 8, 7x1 minus 3x2 plus 5x3 dash minus 5x3 double dash plus x5 equal to 9, x1 greater than or equal to 0, x2 greater than or equal to 0, x3 dash greater than or equal to 0, x3 double dash greater than or equal to 0, x4 greater than or equal to 0, and x5 greater than or equal to 0. Next, we see the simplex method to solve the following LPP. Maximize z equal to 4x1 plus 10x2 subject to constraints 2x1 plus x2 less than or equal to 50, 2x1 plus 5x2 less than or equal to 100, 2x1 plus 3x2 less than or equal to 90, x1, x2 greater than or equal to 0. First step, we will introduce the slack variables x3 greater than or equal to 0, x4 greater than or equal to 0, and x5 greater than or equal to 0. A set of the constraints of the given LPP are converted into the system of equations. Then the modified objective function is z equal to maximize z equal to 5x1 plus 10x2 plus 0x3 plus 0x4 plus 0x5. In step 2, we have to find the initial basic feasible solution, that is xb equal to b inverse b. Next step, we have the table, simplex table. We have to make this table. We have to find all zj minus ej greater than or equal to 0. Here in the first table, minus 4, we have to check the most negative, that is minus 10, that enters the basis. Here we have to find the minimum ratio. Minimum ratio is that is 10 by 5, that is 20. Here the 5 is the pivoted element, so we have to make the pivoted element 0 and all other remaining elements to pivoted element is 1 and all other remaining elements is 0. So the next step, we see the here all zj minus here all zj minus cj greater than or equal to 0, our optimum solution has been obtained. Therefore, the given solution maximum is that equal to 200 and x1 equal to 0, x2 equal to 20. Thank you.